Hey, welcome to the STEP Support Programme Foundation Assignment 17 video solution, where we're looking at sums of squares and cubes and relating them to algebraic expressions. So let's go ahead and read out the first part of the question, where it's given that the sum from r is equal to -1 to n of r squared can be written in this cubic form. And by setting n to be these four different numbers, we need to obtain four equations and show that the sum can be written in this form. So effectively, we need to solve for p, q, r and s. So let's just go ahead and not think about it too much even, and set n to be the values that it tells us to. And actually I'm going to set n to be equal to 0 first, as that's going to end up with some of the terms cancelling, and I think just a simpler answer to start off with. So, but you can do it in any order you want. So let's, for n equals 0, we have that the sum from r is equal to r is equal to -1 to 0 of r squared is equal to, well, we have p times 0 cubed plus q times 0 squared plus r times 0 plus s. So lots of terms cancelling, all of these will cancel out because they've got a 0, and that leads us to have -1 squared plus 0 squared is equal to s, or s is equal to 1. So already we found one of the values that we wanted to find. We found the value of s, and I think we should just continue like this. So let's set n to be -1 and see what we can find. So setting n to be -1, we get that the sum from r is equal to -1 to -1. So that's just going to give us -1 squared is equal to p times -1 cubed plus r times -1 squared plus, that's q, plus r times -1 plus s. So that gives that -1 squared is equal to, so that's minus p plus q minus r plus s. And actually we know the value of s is equal to 1, which we just found. So let's substitute that in and subtract the 1 from both sides to give 0 is equal to minus p plus q minus r. And so we can't do anything with this just yet, but let's number this equation, just as you would with handling simultaneous equations, and then we can come back to this nice and easily. So, again, let's consider n is equal to 1, and do the exact same. It's a bit of a slog to get through, but it will end up with results, as it's what the question told us to do. R squared is equal to p times 1 cubed plus q times 1 squared plus r times 1 plus s. So simplifying this out again, the left hand side we get -1 squared plus 0 plus 1 squared, so that's 2. On the right hand side we get p plus q plus r plus s, which is 1. So subtracting 1 from both sides, we get 1 is equal to p plus q plus r. And that can be equation 2. Now, before we do n is equal to 2, I've noticed that we can add equations 1 and equations 2 to cancel out the p and the r. So just as you would with simultaneous equations, when you add them together to try to cancel out the variables and get an equation in just one of the variables, we're going to do this to get an equation for q. So we can do equation 1 plus equation 2. And let's see what that gives us. Adding the left hand sides is going to give us a 1, and adding the right hand sides is going to give us, well, minus p plus p is 0, minus r plus r is 0, q plus q is 2q. Bit of a tongue twister. So we have 1 is equal to 2q. So we can say that q is equal to a half. So we just solved equations 1 and 2 simultaneously to get q is equal to a half. And we've already found a second one of them. So we're getting nice and quick progress. Now we just need to find r and p. But let's not forget it's told us to do n is equal to 2 as well. So let's go ahead and do that. If the sum from r is equal to -1 to 2 of r squared is equal to p times 2 cubed, q q times 2 squared, r times 2 plus s. So the left hand side is going to be minus 1 squared, 0 squared, 1 squared, 2 squared, all added, which is going to give us a 6 is equal to 8p plus 4q plus 2r plus s. And now we know the values for q and for s. Just as a reminder, s is 1 and q is a half. So let's use those. We have 6 is equal to 8p, just to remove as much complexity as early on as possible, this is. Plus, so we already know what s and q are, so why not get rid of them? And let's simplify this by grouping terms. We get 3 is equal to 8p plus 2r. And let's call that equation 3. So it's looking good. We've got an equation for p and r. And actually, in equation 2 or equation 1, we can eliminate q. So let's eliminate q, i.e. substitute in q is equal to a half, and get ourselves two equations of just p and r. So let's sub q is equal to a half into, let's say 2. Let's just remind ourselves what 2 was. 2 is 1 is equal to p plus 2 plus p plus q plus r. 1 is equal to p plus a half plus r, which gives p plus r is equal to a half. Okay, let's use both of these simultaneously to solve for p and r. These just look like two normal simultaneous equations. So I think I'm going to use the method of substitution here. It seems like it might be a little bit more straightforward, but of course anything's fine. We have r is equal to a half minus p, just by rearranging this one. And then let's sub into 3 to give ourselves, I'll just scroll up a little bit so we can see what it is. 3 is equal to 8p plus 2 times a half minus p. So let's expand things out, group the terms. We have 3 is equal to 8p plus 2, that should be a 1, minus 2p. And we can scroll down a little bit now. We have 2 is equal to 6p, which gives us p is equal to a third. So we found a value for p, and a third seems like as round as we're going to get. That's like, I'm not too worried about that. Let's just find the value for r. So let's use r is equal to a half minus p to give r is equal to half minus a third, which is equal to an eighth. A sixth. Sorry, let's not fail on the algebra right at the end. Yeah, now we have a value for r, p, q and s. Just to summarise, we have p is equal to a third, q is equal to half, r is equal to a sixth, and s is equal to 1. But we're not done yet. Let's just reread the question, see what it wants us to do. It wants us to show that the sum from r is equal to 0 to n of r squared is equal to this. And actually note that we were dealing before with the sum from r is equal to minus 1, and now we have the sum from r is equal to 0. So we're going to need to deal with that at some point. So let's just write out what we already have and see what we can do with it. We have that the sum from r is equal to minus 1 to n of r squared is equal to a third n cubed plus a half n squared plus a sixth n plus 1. So that's the cubic, just by substituting in the values of p, q, r and s. So the cubic that the question gave us here. Okay, now we need to change it from r is equal to minus 1 to r is equal to 0. And we can do that by saying that the left hand side is equal to, actually I think I might write it out separately just for clarity, that we have r is equal to minus 1 to n of r squared is equal to minus 1 squared plus the sum from r is equal to 0 to n of r squared. If you can't see why that is, have a bit of a think about it, maybe without the sigmas. We're replacing the minus 1 term inside the sigma and taking it out, which is of course equal to 1 plus the sum. So let's replace our left hand side in this equation with the value we found here to get that the sum from r is equal to 0 to n of r squared plus 1 is equal to this long cubic, a third n squared plus a half n, sorry, a third n cubed plus a half n squared plus, what was it, a sixth n plus 1. And we can cancel both of these 1's, which is looking good because it's going to help us factorise. So factorising out, let's take the 6th n. I think, well, actually, let's have a look at the question, see if it can give us any hints. And yeah, we can see they're factored out a 6th n, so that might be a good place to start. A 6th n, we have 2n squared plus 3n plus 1. And let's keep going, factorise this. 2n plus 1, n plus 1 I think works. Let's just have a look. So I just did this by inspection, but we could have also had a look at the question and seen what they had and just seen if that worked. So yeah, 2n squared times n, sorry, 2n times n gives 2n squared. Checking the 3n term, we have 1 times n, 1 times 2n, add them together we get 3n, and multiply 1 and 1 and we get 1. So let's just read the question, check that this is the required form. It is. That one. And we're done. So let's write as required. And this is exactly what they wanted. Okay, so let's continue with the second part now. So we're now given a sum of cubics, and it can be written as a quartic, and we want to show this equation. And I think it's first worth noticing that we have an r is equal to minus 2 here, whereas in the first part we had an r is equal to minus 1. And small differences like that aren't coincidences, they're normally intentional and can give you hints towards how you're meant to solve it. And we're not given any kind of other suggestion of how to solve this question, so I think we definitely want to be using a similar technique to the previous part, where we're setting n to be different values to obtain equations. But of course we're not going to have enough information with just 4 equations to find 5 unknowns, or at least it's quite unlikely. So maybe let's consider n is equal to minus 2 as well. So that's minus 2, minus 1, 0, 1 and 2. So then we have 5 different equations, and that might be able to help us solve for 5 unknowns. Again, I'm sure there are other values of n you could take, but I think minus 2 might be the easiest given the question does seem to be hinting towards that number minus 2 a little bit. So yeah, let's crack on with that. So let's set n is equal to 0, and so the left hand side becomes the sum from r is equal to minus 2 to n, sorry, to 0 of r cubed is equal to, all of these terms cancel other than the e, and this left hand side is going to be equal to minus 8 plus minus 1, so that's minus 9 is equal to e. So we already have our value 3, it's looking pretty good. Now let's consider n is equal to 1 and minus 1. Let's do n is equal to 1 first. We have the sum from r is equal to minus 2 to 1. So that's just going to be adding 1 cubed to the previous one. And the right hand side is going to be equal to a plus b plus c plus d plus e, because 1 to any power is equal to 1. Okay, so we've figured out that the left hand side is just minus 9 plus 1, so minus 8 is equal to, and we can substitute in our value for e, a plus b plus c plus d minus 9, and finally if we add 9 to both sides we get 1 is equal to a plus b plus c plus d. And you might be able to get the idea now that time might be one of our biggest struggles, so I'm going to try to get through the algebra as quickly as possible. Still showing sufficient steps, but yeah. So yeah, n equals minus 1 now. we have the sum from r is equal to minus 2 to minus 1 of r cubed is equal to, okay, now we have a minus b plus c minus d, and then a plus e. And that's just by evaluating minus 1 to the 4 to the 3 to the 2, etc. to find the coefficients. And then on the left-hand side we have a minus 8 plus minus 9, so plus minus 1, so that's minus 9 again. And we have a minus b plus c minus d minus 9. And again, if we add 9 to both sides, that minus 9 was just from our value of e, we get 0 is equal to a minus b plus c minus d. Okay, let's number this equation 2. And it's fine to be reusing numbers. I think it's clear they're different equations given we're on a new part now. And if you remember, last time we found kind of our other equation by adding these. Also subtracting does give us an equation in just b and d. So it might be worth doing both of these, as they do kind of reduce our 4 equations of 4 variables to 2 equations of 2 variables. And I know that the equations of 2 variables do seem like they'll be a bit simpler. So let's go ahead and do that. So let's say equation 1 plus equation 2 gives us, okay, the left hand side is going to be a 1, and the right hand side is going to be 2a plus 2c. And that might be easier to write as a half is equal to a plus c. And 1 minus 2 is going to give us similar, but with 1 is equal to 2b plus 2d this time. And that's again going to give us a half is equal to b plus d. Perfect. So now there's not much we can do with these currently, so I think we're just going to substitute in the other values of n, then we can kind of worry about what we're going to do next. But I think it's nice to simplify down those 2 questions early on. So yeah, n is equal to 2, let's do first. So we have the sum from r is equal to minus 2 to 2 of r cubed is equal to, okay, let's have a look at what this right hand side is going to be. We have 2 to the 4, which is equal to 2, 4, 8, 16, and then the others kind of follow. So we have 16a plus, plus 8b plus 4c plus 2d plus e. And again, just simplifying this, we get, okay, we can notice that r cubed is actually an odd function. So because it goes from minus 2 to 2, this just equals 0. I mean, or you can just evaluate it manually if you want. We don't need to show any working for that. And we have 16a minus 8b plus 4c plus 2d minus 9. Move the 9 over to the other side, and we get this. And sorry, I've just noticed that this should be a plus. Don't know where I got that minus from. Yeah, sorry about that. Yeah, we are dealing with positive 2 here. And let's call this equation 3. And finally, n is equal to minus 2. This is kind of our novelty that we decided to do on this part. And we go from r is equal to minus 2 to minus 2 of r cubed is equal to, now we have the minus signs, 16a minus 8b plus 4c minus 2d plus e. Okay, the left hand side is just going to be minus 2 cubes, that's minus 8. And the right hand side, we can substitute in our value for e. We can actually move it over to the other side now, so we can replace that with a 1. Just trying to get through this algebra a bit faster. Plus 4c minus 2d. Pretty much there. We have a 4. This is equation 4, I mean. Okay, that should be a 1. Now, I think we've got kind of similar looking pluses and minuses, like being the only difference between 3 and 4. So I think just doing the same as we did with 1 and 2, add and subtract them, get some more equations. In terms of just 2 of the variables. So let's take 3 plus 4. And this gives us the left hand side as being 10 and the right hand side as being sorry, made another mistake. That should be an A here. Sorry about that. And on the right hand side, sorry, the left, yeah, right hand side, we've got 32a plus 8c. And again, I think we can divide it down a little bit. We have 5 is equal to 16a plus 4c. And finally, we have 3 minus 4. Gives the left hand side as being an 8. And the right hand side as, well, the a's and the c's are going to cancel this time, and we have 16b plus 4d. And again, we can simplify that down a bit to get 4, actually we can divide the whole thing by 4 to get 2 is equal to 4b plus d. Okay, so we're slowly getting there. I think I'm just going to scroll up now and compare these to our other equations, maybe copy them down here. And I hope you noticed that all we've been doing is just solving like 5 simultaneous equations, which is a bit horrible, but the numbers work out okay, or have been so far. So, okay, what do we have? We have half is equal to a plus c and a half is equal to b plus d. So let's copy them down here. So we have half is equal to a plus c and a half is equal to b plus d. I believe were our equations. They are. So let's just make it clear where these came from for any examiner. And maybe I'll just put them in their own box. Okay, so we've got 4 equations of just 2 variables each. That's looking a lot nicer than our 4 equations, 4 variables. Let's see what we can do. I think I'm liking the look of this just d on its own. So let's see if we can do something with these 2 equations in b and d. So I might say that this is d is equal to 2 minus 4b, and then we can use substitution. So let's sub into, I think I should have named these equations I've in boxes. So let's at least see where it came from. The half is equal to b plus d, just so I can easily refer to it. That was 1 minus 2, and the other one was 1 plus 2. So I'll just write that down. Perfect. So yeah, let's sub this into 1 minus 2. So it's getting a bit messy, the algebra, but I think if we just press on, it will come out something nice, hopefully. We have a half is equal to b plus 2 minus 4b. That's the substituting in our value for d, which gives us that 3b, moving the b's over to the other side, is equal to 3 over 2. So b is equal to a half. And then we can just substitute this into our equation for b and d. So a half is equal to a half plus d, which gives d is equal to 0. Okay, getting there. Got 2 of the values, just need to find a and c now. So I think again substitution's probably the best bet. So let's rearrange this 1 plus 2 here and see what that can give us. So we have a half is equal to a plus c. 1 plus 2. A half is equal to a plus c. Gives us, just so we can substitute something in, we have a is equal to a half minus c. And now let's see if we can substitute this into 3 plus 4. So that's this equation here. So that's 5 is equal to 16a plus 4c. Sub into 3 plus 4 to get 5 is equal to 16a. That's our value for a, plus, I think it was 4c, was it? Yeah, plus 4c. Perfect. Okay, I'm kind of wishing that I'd rearranged for c to be the subject earlier, but oh well. Either ways work. We have 5 is equal to 8 minus 16c plus 4c. Let's rearrange this to get the c's over on the other side, and we have 12c is equal to 3, or c is equal to 1 over 4. Finally, just need to get one more left. So we have half is equal to a plus c, which gives us that a half is equal to a plus a quarter, which gives us that a is also equal to a quarter. Okay, so we found our values for A, B, C, D and E. And now if we just reread this bit of the question, we want to show that the sum from, again, r is equal to 0, not minus 2 this time, is equal to this kind of factorised quartic. So okay, let's go ahead and find some kind of expression for this sum of cubes on the left hand side from r is equal to 0 by using sum from r is equal to minus 2 to n of r cubed. So let's just recall what our values are. So we have a quarter n to the 4 plus what was b, so yeah, that quarter was our value for a, and again here I'm just substituting in for the a, b, c, d and e here, which are equal to this sum from r is equal to minus 2 to n. B is equal to, I underlined it somewhere, a half, plus a half n cubed, plus c is again a quarter, n squared, plus I believe d was 0. Yeah, so we can ignore that term actually. And then e, right back at the start, was minus 9. So let's cross that one out and we get minus 9. Okay, let's now find some kind of way to relate this sum from minus 2 to a sum of 0. So just exactly the same as last time. We have the sum from minus 2, r is equal to minus 2 to n of r cubed is equal to the sum from r is equal to 0 to n of r cubed. And then if we add to that the term for minus 1 and the term for minus 2, so that's minus 2 cubed plus minus 1 cubed is equal to kind of this sum that we want to find, plus, or actually, should I say minus 9. And that's minus 8 plus minus 1. Okay, perfect. Now, almost there. We can say that this whole thing on the left hand side is equal to the sum from r is equal to 0 to n of r cubed minus 9. And then the right hand side stays exactly the same as this quartic, plus half n cubed plus a quarter n squared minus 9. All that is left now, let's add 9 to both sides. I was thinking that 9 looked a bit big, so it's good we've got rid of that. Okay, now we just need to factorise. So on the home stretch, I think probably a good place to start would be let's factorise out. Actually no, let's look at the required form. I think that kind of saves us a bit of thinking. We want there to be a quarter n squared factorised out, and the other one should happen to be an n plus 1 squared. Okay. We do still need, remember it's a show that question, so we do still need to show it. We can't just copy it down and like kind of hope that it's right. So let's factorise out the quarter n squared. We get a quarter n squared, and we get a n squared plus 2n cubed, oh sorry, plus 2n, plus 1. And then if we factorise this, we do, as required, get, after all of this algebra, and then plus 1 squared. And there we are, so we can say as required. So it was some long algebra, and I think probably part of the difficulty there is making sure you can do it to time and come up with all of these like small ideas just in the time. But we got there, and yeah, bye.